So in this problem set, we're going to cover material on the linear approximation, extrema, and the method of Lagrange multipliers. I'm going to work through some of these problems in this video, but I'm not going to get through them all. So you can see the solutions to all of the problems, which I'll post on the Moodle webpage. Let's take a look at question 1. So we've got a right-angled triangle. The two short sides, we'll call them x and y. We know them to an accuracy of 2%. The question then is, if we use that to calculate the area of the triangle, what's the maximum possible percentage error in our calculated value? So let's set that problem up. So let's call the two sides x and y, the opposite and adjacent sides. I know that the error in these measured values here is going to be 2%. So let's express that as a ratio. So delta x over x has got to be less than or equals to 2% or 0.02. Notice that I'm using the absolute values there because this is the maximum possible error in x. And likewise, delta y over y is less than or equals to 0.02. We also know that the area of this triangle is a half the base by the perpendicular height. So the question is, what's the maximum possible percentage error in our area A? So this is the maximum possible error, so we need to use the inequality which we saw in class. So that is that the maximum possible error, delta A, the error will be less than or equals to partial derivative of A with respect to x multiplied by the error in x, and we need to put absolute value signs on all those, plus partial derivative of A with respect to y multiplied by the error in y. So again, you notice that we're using the maximum possible error expression here. So it's got a less than or equal sign, and everything has absolute value symbols on it to indicate that all of the errors have to combine to give us the maximum possible error. So let's see what dA dx is and dA dy is and substitute those expressions into this formula. So we have this is equal to dA dx, which was 1/2 times y multiplied by dx, plus dA dy, which is 1/2 times x multiplied by dy, or delta y. Alright, so you notice that we have a sort of an interesting problem here because we don't actually know what the values of x and y are. All we know is that the relative errors in x and y are 2%. That's the only piece of information that we're given. So what we're going to see is that because we're only looking for the maximum possible percentage error, that is, we're looking for the error in A as a ratio with respect to the value of A, we don't actually need to know what the values of x and y are. So let's see that. So we're looking for the ratio of the error in A divided by A itself. So we saw that that was less than or equals to 1/2 times y. Y is a positive number there, so I don't have to worry about the absolute value symbol. Delta x could be positive or negative, so let's keep that absolute value symbol there. Plus 1/2, x is also a positive number, it's a length, so that can be taken outside of the absolute value symbol. Delta y can be positive or negative. I'm going to divide this whole thing by the area. So the expression for the area was 1/2 x times y. So let's see what that expression then becomes when I do some cancellation. I've got 1/2 y delta x divided by 1/2 xy. So you can see that a factor of 1/2 x, will 1/2 times y, will cancel with the factor of 1/2 times y, and leave me with delta x divided by x. Likewise, you notice here I've got 1/2 x times delta y, all divided by 1/2 x times y. So the x's there will cancel, the half will cancel, and I'm left with delta y all divided by y. Again, remember that x and y themselves are positive numbers, so it doesn't matter that I don't have the absolute value symbols here. I can put them back on if I want. And you see that I have expressed the relative error in the area entirely in terms of the relative area of x and the relative area of y, or the relative error in y. So we know what those are. They're both 2% or 0.02. So this is equal to 0.02 plus 0.02, which is equal to 0.04. Or if I wanted to express that as a ratio, as a percentage, I'd have to multiply that by 100%. So we see that the maximum possible relative error is 4%. Maximum possible percentage error. And so that's actually going to be a very useful technique for calculating percentage errors when we don't know the exact values of the variables that we're dealing with, when we only know those errors as percentages as well. Okay, let's take a look at the next problem. I'm going to skip to question 5. This is a question on stationary points. So here we have a function 2x cubed plus 3x squared y plus y squared minus 1. We need to find the stationary points of that value, of that function, and determine whether they're max, min, or saddle points. So this is question 5. And I'm going to start with part 1 of this question. So in this question, the function we're dealing with is z is equal to 2x cubed plus 3x squared times y plus y squared minus y. Okay, so we want to find the stationary points of that. So the first thing that we're going to need to do is take the partial derivatives of this function with respect to x and with respect to y and set it equal to 0. Okay. So the partial derivative of z with respect to x is equal to 2 times 3x squared, so 6x squared, plus 3 times 2x, that's 6x times y, and that's going to be equals to 0 at the stationary points. The partial derivative of z with respect to y will be equals to 3x squared plus 2y minus 1. And that will also be equals to 0 at the stationary point. So now I have 2 equations for 2 unknowns. I'm going to solve those, but I have to be careful that I don't divide by 0, that I actually capture all of the solutions to this problem. So let's take a look at that first equation. You notice that I can take out a factor of 6x. So I get 6x times x plus y is equal to 0. And there's no factor that I can take out of the second expression, but I can rewrite it as an expression for y in terms of x. So let's rewrite both of these expressions here. Expression number 1 and expression number 2 in slightly more useful form. So expression number 1 is going to give me, if I get rid of that factor of 6, I get x times x plus y is equal to 0. And we remember that if we have something times something equals to 0, then one of those things has to be 0. So that means that either x is equal to 0 or x plus y is equal to 0. So let's label those two options there. Let's call them 3a and 3b. We also have that from expression 2, that if I do a little rewriting here, I get 2y is equal to 1 minus 3x squared. Or if you like, y is equal to 1/2 minus 3 over 2 x squared. And let's call that expression 4. So what we have here is a couple of different pieces of information that we need to combine to find our solutions. Now remember that expressions 3a and 3b, those came from equation 1. So that came from the partial derivative of z with respect to x was equal to 1. Now I need to use at least one of those pieces of information in order to satisfy equation 1. Expression 2 just ended up giving me expression 4. So I have a couple of different possibilities. I have 3a combined with 4 or 3b combined with 4. Those are the two different possibilities which will satisfy both of these equations, 1 and 2. So let's start off by looking at 3a and 4. So combining 3a and expression 4, we see so x is equal to 0, which means that substituting that into 4 just gives me y is equal to 1/2. So I immediately get my point x is equal to 0, y is equal to 1/2. That's our first stationary point. The second possibility is 3b combined with 4. So 3b and 4. So in 3b, we found that x was equal to minus y, or y was equal to minus x. So if I substitute that into expression 4 to eliminate y, I get a single expression for x. It's a quadratic expression. So let's solve that quadratic. I guess I have to multiply up by the 2 again. So that's going to give me minus 2x is equal to 1 minus 3x squared. Bring that 3x squared over to this side. And now let's factorize that. So we could have 3x, x, and I guess we can have 1, and we can have 1, and then we can choose plus or minus. So we want 3 plus 1 times x minus 1. So just check that. We've got 3x times x is 3x squared. We've got 1 times minus 1 is minus 1. And I have 3x times minus 1 is minus 3x, plus x is minus 2x. So those are the factors of that quadratic. You can do that however way that you are most comfortable with. So again, we've got something times something equals to 0, which gives me two different possible solutions. So this implies that either 3x plus 1 is equal to 0, or x minus 1 is equal to 0. So once more, we have two different possibilities here. Let's start off with the first possibility here. 3x plus 1 is equal to 0. that gives me x is equal to minus a third. The other possibility that x minus 1 is equal to 0, that just gives me x is equal to 1. So those are two different possibilities for x. Now let's go back and substitute in those expressions into our expression for y. Remember that y was equal to minus x in this case, so it's equal to 1/3 for x is equal to minus a third, and it's equal to minus 1 for x is equal to 1. So that gives us two sets of points. We've got x is equal to minus a third, y is equal to a third, and x is equal to 1, y is equal to minus 1. So we have 3 points: 0, a half, minus 1/3, 1/3, and 1 minus 1. Now what we're going to have to do is calculate the second derivatives of our function and substitute those into our formula for d to find out if this is max-min or saddle point. So let's quickly remind ourselves what the second derivatives of this function are. So the first derivatives, let's bring those down from further up the page. We had 6x squared plus 6x times y. We had the y derivative was 3x squared plus 2y minus 1. So the second derivative with respect to x will be 12x plus 6y. Second derivative with respect to y will be 2. And the mixed derivative will be equals to, well, we can choose either the y derivative of this expression or the x derivative of this expression. It gives us the same thing by the mixed derivatives theorem. So if we take the y derivative of this expression, we get 6x. So those are our second derivatives. Let's now calculate what those are for our different points. So the first point that we had was 0, a half. So for the point 0, 1/2, substituting x is equal to 0 and y is equal to a half here, we get that the second derivative with respect to x is equal to 0 plus 6 divided by 2, which is 3. The second derivative with respect to y, well, that's the same. It's just going to be equals to 2. And the mixed derivative, 6 times x, well, x is equal to 0, so this is equal to 0. So those are our second derivative with respect to x, second derivative with respect to y, and the mixed derivative. We're ready now to put these together into our function d. So d, remember, was second derivative with respect to x multiplied by the second derivative with respect to y minus the mixed derivative squared. So in this case, it's going to be equals to 3 times 2 minus 0 squared. So that's equals to 6, which is greater than 0. So when d is bigger than 0, it means that our contours are closed, which implies that we're dealing with a max or a minimum. But we know that both the second derivative with respect to x and the second derivative with respect to y are both positive numbers. If either of them were positive, it would tell us we're in a minimum. Or more accurately, a local minimum. The last step here is to calculate what the value of our function is at that point. So, sorry, we're talking about z at x is equal to 0, y is equal to a half, substituting that into our expression for z, 2x cubed plus 3x squared times y plus y squared minus y is equal to 0 plus a quarter minus a half, which is minus a quarter. So in other words, we have a local minimum at x is equal to 0, y is equal to a half, and z is equal to minus a quarter. Let's move on to the second of our stationary points. That was minus a third. So we're again going to substitute this expression into our second derivatives for z. So we have the point minus 1/3. The second derivative with respect to x was 12x plus 6y. Which was equal to 12 times minus a third plus 6 times a third, which is equal to minus 4 plus 2, which is minus 2. We've got the second derivative of z with respect to y. That was just equals to 2, it didn't depend upon x and y. And we've got the mixed derivative. zxy is equal to 6x, which is 6 times minus a third, which is minus 2. Alright, so let's put those into D, see if this thing is a maximum or a saddle point. So D was equal to zxx, zyy minus zxy squared. So zxx was minus 2, zyy was 2, and we've got minus 2 squared. So that's equal to minus 4 minus 4 squared, which is equal to minus 8. That's less than 0, which implies that this thing is a saddle point. I don't need any more information. If D is less than 0, I know I'm dealing with a saddle point. Last step is to calculate what Z is at this point, so minus a third. So that's equals to 2 times minus a third cubed plus 3 times minus a third squared times a third plus 1/3 squared minus 1/3. So that's going to be equals to 2 times minus a third squared is 1/27 plus minus a third squared times a third, so that's going to be plus 3 times 1/27 plus 1/9 minus a third. So that's equals to minus 2/27. Let's put everything over 27 plus 3/27 plus 3/27 minus 9/27. So we've got minus 2 plus 3 minus 9, so that's equals to minus 11 plus 6, which is minus 5/27. So let's summarize that. We found that we have saddle point at the point x is equal to minus a third, y is equal to a third, and z is equal to minus 5 over 27. Okay, last point. So this is the point 1 minus 1. Point 1 minus 1. Again, I've got to calculate all of those second derivatives. So zxx was 12x plus 6y. Which is equal to 12 times 1 plus 6 times minus 1, which is equal to 6. Zyy was just equal to 2. And zxy is equal to 6 times x. So that's equals to 6. So our function d, zxx times zyy minus zxy, that's going to be equals to 6 times 2 minus 6 squared. So that's equals to 12 minus 36. It's equal to 24 minus 24, which is less than 0. So we're dealing with the saddle point again here. Once again, our last step is to calculate the value of our function at the point. So we've got 2 times 1 cubed plus 3 times 1 squared times minus 1 plus minus 1 squared minus minus 1, which is equal to 2 minus 3 plus 1 plus 1. So that's 4 minus 3, which is 1. So we have a saddle point at x is equal to 1, y is equal to minus 1, and z is equal to 1. Okay, so that's question 5, part 1. Let's take a look now at question 5, part 2. So, question 5, part 2 is find the maximum and minimum distances from the origin to the ellipse 5x squared minus 6xy plus 5y squared equals to 8. We're going to use the method of Lagrange multipliers to do this. So let's draw a little sketch of what's going on here. This is question 5, part 2. We have a formula for an ellipse. It's given by 5x squared minus 6xy plus 5y squared is equal to 8. If I just draw this in the xy plane, then my ellipse might look something like that maybe. And we want to find the maximum distance and the minimum distance from the origin to the ellipse. Okay, so the first thing we need to do is identify what is the thing we're maximizing or minimizing, and what is the constraint. So it's clear that we're looking for the maximum or minimum distance of the origin to the ellipse. So the thing we're maximizing or minimizing is going to be distance. So f of x, y is going to be the distance between the origin and a point x, y. Because the point x, y is lying on our ellipse. Let's draw. That looks like maybe it's this point here. So the distance between the origin and the ellipse, that's the thing I'm looking for the maximum or minimum values of. Now we saw in the lectures that using the distance formula, square root of x squared plus y squared, ends up being much more complicated than it really needs to be, because we end up having to take the derivatives of square roots. So what I'm actually going to do is, to sort of make life easier, we're instead going to use not the distance, but the square of the distance. So f of x and y is equal to x squared plus y squared. And we saw in class that the reason that we could do that was because the values of x and y that make the distance maximum or minimum are also the values of x and y that make the distance squared the maximum or minimum. So the distance and the distance squared are equivalent for the purposes of maximizing or minimizing. So that's our f of x and y taken care of. What about the constraint, g of x and y equals to 0? Well, our constraint here is that whatever this point is, x, y, it has to be on the ellipse. It has to satisfy this expression here. So I'm going to rewrite this expression so it has the form something 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 equals to 0. So our constraint is g of x and y is equal to 5x squared minus 6xy plus 5y squared minus 8 is equal to 0. So again, you notice that all I've done there is I've rewritten my expression for the ellipse so that it's something 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 equals to 0. And that's our constraint. Okay, now we're in a position to calculate what the function L is. L of x, y, and lambda. It's going to be equals to f of x and y, the thing we're maximizing or minimizing, minus lambda g of x and y, the constraint. So that's going to be equals to x squared plus y squared minus lambda of 5x squared minus 6xy plus 5y squared minus 8. Now we can start taking derivatives of this. So we're looking for the stationary points of this function. So L subscript x, partial derivative with respect to x, that's going to be given by 2x minus lambda times the derivative of 5x squared, so that's lambda times 10x, or 10 lambda x, plus lambda times 6y, so 6 lambda y, and that's equals to 0. We want partial derivative of L with respect to y is equal to 2y plus 6 lambda x minus 10 lambda y is equal to 0. And of course we also have L subscript lambda is equal to minus 5x squared minus 6xy plus 5y squared minus 8 is equal to 0. So as usual, that just gives us back our constraint. Okay, so we've got three equations here for three unknowns. We're going to solve these now, and the way I'm going to do that is by rewriting those first two expressions. So let's call those expressions 1 and 2. We'll call this one expression 3. Of course, that's just the constraint again. So let's take 1 and divide out a factor of 2. So that gives me x minus 5 lambda x plus 3 lambda y is equal to 0. Okay, so let's take out a common factor of x there in that first two expressions. X 1 minus 5 lambda plus 3 lambda y is equal to 0. Likewise, let's look at expression 2. And divide that by 2 as well, so I get y plus 3 lambda x minus 5 lambda y is equal to 0. Again, I can take out a common factor there, so I'm actually going to take out a common factor of y, 1 minus 5 lambda plus 3 lambda x is equal to 0. So here are our two expressions that we want to solve simultaneously. The way I'm going to do this is by multiplying one of these expressions by 3 lambda. One of these expressions by 3 lambda y, and one by 1 minus 5 lambda x. Okay, so let's call these two expressions 3 and 4. So here's 3, and here's 4. Let's take expression 3 and multiply it by 3 lambda. Let's just multiply it by 3 lambda, actually. That should be enough. And then that gives us x times 3 lambda times 1 minus 5 lambda plus 3 lambda times 3 lambda times y is equal to 0. Now we have to be careful, of course, because I have to make sure I'm not multiplying by anything that's equals to 0. So we have to ask ourselves, is it possible that lambda is equal to 0 here? And of course, that's not allowed here because I'm not allowed to set lambda is equal to 0, because that would mean I was just looking for the global maximum or minimum. I'd be turning off the constraint. Let's take a look at expression 4. What I'm going to do is I'm going to multiply this one by 1 minus 5 lambda. So that's going to give me y times 1 minus 5 lambda squared plus 3 lambda 1 minus 5 lambda times x is equal to 0. And I need to ask again, am I possibly multiplying by something equals to 0 here? And that is a possibility here. It is possible that lambda is equal to 1/5. So I'm going to have to set aside that possibility here. I'm going to set lambda is not equals to 1/5. And I'm going to have to revisit that later and see if that changes things. But for the time being, let's stick with what I've got. I now have two expressions here that I can subtract from one another. So let's subtract the bottom expression. Let's put some minus signs on it so we get minus, minus. And I'm going to subtract these two expressions. You see that this expression here cancels with this expression here, giving me a single expression for y in terms of lambda. So that's going to give me 9 lambda squared minus 1 minus 5 lambda squared all times y is equal to 0. I can tidy that up a little bit, so we get 9 lambda squared, slight mistake there, that's squared outside the brackets. So then we get minus 1 plus 10 lambda minus 25 lambda squared times y is equal to 0. So that's last step here. I can take out a factor of minus. 25 minus 9 is 16 lambda squared plus 10 lambda minus 1 is equal, multiplied by y is equal to 0. So you notice here that I have two possibilities. I've got either that this term in square brackets is 0, or I've got the y is equal to 0. So this implies that either y is equal to 0 or 16 lambda squared plus 10 lambda minus 1 is equal to 0. So if y is equal to 0, what are the consequences of that? Let's go and revisit one of our equations up here. Let's revisit equation 4. So remember, equation 4 said that y times this plus 3 times this, 3 lambda x, was equal to 0. So if y is equal to 0, you notice that this term goes away, and I'm left with 3 times lambda times x is equal to 0. So if y is equal to 0, implies that lambda times x is equal to 0, which implies that either lambda is equal to 0 or x is equal to 0. But again, we remember that lambda is equal to 0 is not allowed, because that would be the unconstrained problem. So we get the solution x is equal to 0, y is equal to 0. But let's think about that solution for a minute. What it's telling us is that the distance is minimized when we measure, the distance between the origin and xy is minimized when I take xy to be 0, 0. But that's just a distance of 0, and that obviously doesn't sit on the ellipse as we've drawn it. So you can see that the solution x equals to y equals to 0 doesn't satisfy this equation. It doesn't sit on this ellipse. So in fact, this has given us a spurious solution. So this solution we can reject because it's not actually a solution of our constraint. It doesn't satisfy our constraint. So we see that the possibility that y is equal to 0 is not allowed. So instead what we've got to do is go back and look at the other possibility, which was that x squared lambda, 16 lambda squared plus 10 lambda minus 1 was equal to 0. So let's take a look at that. So we can factorize that. That gives us factors of 4 lambda, There's a slight error here somewhere. Ah yes, I made a slight error here. So I took out a minus sign, that this should have become a minus sign. That's a plus sign. There we go. That's better. Yep. Okay. So let's correct that down here. That's supposed to be a minus and a plus. All right. So let's factorize this. We're going to get minus 4 lambda, 8 lambda minus 1, 2 lambda. Put a minus sign on that, a minus sign on that, plus, that's fine, is equal to 0. So let's just check that. We see that we get minus 8 lambda times minus 2 lambda is 16 lambda squared. 1 times 1 is 1. And we have minus 8 lambda minus 2 lambda is minus 10 lambda. So we see that we have two solutions here. We've got lambda is equal to 1/8, or lambda is equal to 1/2. Alright, so we've got solutions for lambda there. Let's go back and take a look at our original expressions for x and y in terms of lambda. We're going to substitute those expressions, those values of lambda, into those equations there to get an equation for x in terms of y. And then we're going to substitute that into our constraint and solve for x and y. So let's start off with lambda is equal to 1/8. So we're going to substitute that into, let's say, equation number 3, which was x times 1 minus 5 lambda plus 3 lambda y. So equation 3 implies x times 1 minus 5 lambda plus 3 lambda y was equal to 0. Let's substitute in the value lambda is equal to 1/8, which gives us x times 1 minus 5/8 plus 3 over 8 y is equal to 0. So x times 1 minus 5/8 is 3/8. 3 over 8y is equal to 0. Those factors of 3, 8 cancel, and that gives me that x is equal to minus y. Let's go back to our constraint. Our constraint was equation, it was 5x squared minus 6xy plus 5y squared is equal to 8. Substitute in x is equal to minus y to get 5 minus y squared minus 6 times minus y times y plus 5y squared equals to 8. And you notice that this is a single expression for y. So we end up with minus 5y squared plus 6y squared plus 5y, that's a plus 5y squared, plus 6y squared, plus 5y squared, which is 16y squared, is equal to 8, which implies that y squared is equal to 1/2. And that gives me that y is equal to plus 1/2, or y is equal to minus 1/2. And we remember that x was equal to minus y, so that means that x is equal to minus 1/2, square root of 1/2. and y is equal to plus a half, or y is equal to minus a half, and x is equal to plus a half, 1 over the square root of 2. So we get 2 points. We get 1 over root 2 minus 1 over root 2, and we get minus 1 over root 2, 1 over root 2. Okay, that deals with the possibility that y was equals to 1/8, so let's tick that one. We now need to look at the other possibility, that lambda was equal to a half. So lambda is equal to a half. Again, I'm going to substitute that in to x times 1 minus 5 over 5 times lambda plus 3 lambda y is equal to 0. So substituting in lambda is equal to a half, we get 1 minus 5 over 2 lambda, 5 over 2, plus 3 over 2y is equal to 0. 1 minus 5 over 2 is minus 3 over 2. I can cancel those factors of 3 over 2 to give me minus x plus y is equal to 0, which means that x is equal to y. So let's again substitute that straight into our constraint. So the constraint was 5x squared minus 6xy plus 5y squared was equal to 8. And we've just seen that x is equal to y, so I get 5y squared minus 6y squared plus 5y squared. So that's going to be 5 minus 6 plus 5, that's 10 minus 6 is equal to 4y squared, and that's equals to 8. So you see that that's going to give me y squared is equal to 2, which gives me two different possibilities. Y is equal to plus the square root of 2, or y is equal to minus the square root of 2. And again, we've just seen that x is equal to y in this case. So that means that y is equal to plus 2 implies that x is equal to plus root 2. Y is equal to minus root 2 implies that x is equal to minus root 2. So that gives us the points root 2, and minus root 2, minus root 2. Okay, so we now have our 4 points. Let's gather them all together and see which of them is the maximum distance and which one is the minimum distance. So we have the points 1 over root 2 minus 1 over root 2, the point minus 1 over root 2, 1 over root 2, and I have the point square root of 2, square root of 2, and I've got the point minus the square root of 2, minus the square root of 2. So we want to find the distance. So the distance again was the square root of x squared plus y squared. So for my first point there, 1 over root 2 minus 1 over root 2, I'm going to get the square root of 1/2 plus 1/2. I get the square root of 1, which is 1. For the second point, I get the square root again of 1 over 2 plus 1 over 2. I get a distance of 1. For the third point, I get the square root of 2 plus 2, get the square root of 4, which is 2. And for the fourth point, I get 2 plus 2, square root of 4, I get a distance of 2. So you can see that there are two sets of points that are minimum distance and two sets of points which are the maximum distance. So we can represent this now in our xy plane, draw a picture of what this actually looks like. So we've got x and y axis. I've got the point square root of 2, square root of 2, let's put that there. I've got minus the square root of 2, minus the square root of 2, let's put that there. I've got the point x is equal to plus 1 over root 2, y is equal to minus 1 over root 2. And I've got the point x is equal to minus 1 over root 2, y is equal to 1 over root 2. So those are the 4 points that are closest and furthest away from our origin. And they all lie on the ellipse. So they all lie on the constraint. So you can see that the closest distances will correspond to those 2 points, and the furthest distances will correspond to those 2 points. Now, before we finished here, we should go back and take a look at that possibility that we kind of ignored for a second back there. We talked about the possibility that lambda was equal to 1/5. So this possibility here. Let's just make sure that we haven't thrown away an important solution there. So let's think about what would that imply if we were to substitute it into expression 4, for example. So the question we want to ask is, what about lambda is equal to 1/5? Well, we saw that expression 4 told us that y times 1 minus 5 lambda plus 3 lambda x was equal to 0. But if I put lambda is equal to 1/5 in here, you can see that this expression will be 0 if lambda is equals to 1/5, which leaves us with 3 times lambda, which is 3/5 x, is equal to 0, which implies that x is equal to 0. Okay. Let's also look at what would happen if I substituted that into expression 4. In expression 3, so expression 3 was x times 1 minus 5 lambda plus 3 times lambda y equals to 0. Again, if lambda is equals to 1/5, that expression there will be 0, and I'm left with 3 times lambda, so 3 over 5 times y is equal to 0, which again gives me y is equal to 0. So we've seen that So that implies lambda is equal to 1/5 implies that x is equal to 0, y is equal to 0. But we've already seen that the point 0, 0 is not on the ellipse. It doesn't satisfy the constraint. So it's a disallowed point, so it's not allowed. So lambda cannot be equal to 1/5. So sometimes in these Lagrange multiplier problems, we have to be careful to make sure that we haven't gotten rid of a possible solution. In this case, I ignored that solution until the end and then showed that it in fact is not a solution, even though it seemed like it might be at the time.